I always like to talk about this topic. The reason is that it is a combination of statistics and statistical issues, how to estimate those things, but it's also very much related to interpretation. I think the interpretation is even more difficult than the actual analysis. But let me start by introducing myself. So I currently work at the Oxford University Clinical Research Unit in Ho Chi Minh City in Vietnam. So this is a unit from the University of Oxford. It's completely devoted to the study of infectious diseases, and it is located at the compound of the Hospital for Tropical Diseases. According to the head of the unit, this hospital is the largest hospital in the world that only focuses on infectious diseases, and there are still a lot of infectious diseases in Vietnam, more than in Europe. A little bit more about my earlier background. So my background is in mathematics. I did my PhD in mathematical statistics, and after that I have been working in a medical research environment the rest of my life. I did a lot of work on infectious diseases, in the beginning very much on HIV/AIDS, and at the moment I still mostly work on infectious diseases, of course, because that is the unit, the top research topic of this unit, but it's no longer very much on HIV. Okay, let's start. So what I will do in those, say, 40 minutes, I will say a little bit about what competing risks are. So I try to explain what it is. I will explain the basics of analysis. I won't go into the technical details, but there are different ways to approach the problem. And then in the final part, which is more as a summary, but I will also focus on how to interpret in relation to the different choices that can be made in the presence of competing risks. So before going to competing risks, I don't know, I guess the background of the listeners varies quite a lot. So maybe some of you have hardly any experience with standard survival analysis. So let me give a very brief overview of standard survival analysis. Here is a figure, it's a Kaplan-Meier figure, which gives the typical situation of survival analysis. It is in fact about survival, mortality. It's not survival with respect to age, but it's survival after HIV infection. And there are two different groups, those that were followed before 1996 and after 96. These are data from my earlier work environment, from the Public Health Service in Amsterdam. And those data were obtained from cohort studies. So in a cohort study, individuals are followed over time. And what you will typically observe in cohort studies, because of the time component, that not all individuals will have the event observed, certainly for mortality, which can happen over a time frame of decades. In the study, you will find individuals that didn't die. And some of them may have even been followed up for a very short period. So let's say now we are in 2020, an individual that became HIV infected in 2018, of course, only can have 2 years of follow-up maximum. So a problem is that we have to deal with those, what I call right-censored data. And for that issue, for that problem, the hazard or the rate is a very important quantity. So the two main concepts, quantities in survival analysis are the risk and the rate. So the risk, that is what was plotted in the previous figure, the probability to have the event before a time t, or the survival, the probability to remain event-free. And the hazard is a conditional probability. So it is the probability to have an event, given that you are still event-free at that time point. I use the notation H for this hazard, and there are two different situations. Either the distribution in which we are interested is discrete, so there's only a finite number of possible values, or it is continuous. I think continuous is the more frequently occurring situation, but the discrete one is a little bit easier to interpret. The nice thing is, and that is why the hazard is important, once you know the hazard, you also know the risk. And let me give an example. So here's mortality as endpoint. I look over the different years, and some individuals were followed for only 1 year, 2 years, and so on. So how are we going to estimate the probability to survive up till a certain year, to remain alive, say up till year 6? Well, what we are going to do is to split up the timescale. Because in every year, some individuals are censored, and how do we deal with them? We cannot say, well, they remained alive until the end of the 6-7 years period. So we are going to use a law of probability. The probability to remain alive for at least 6 years is a product of conditional probabilities. So the probability to survive the first year, the probability to survive the second year, given that you were alive at the beginning of that year, and so on up till year 5 to 6. And each of them is formulated or is quantified through the hazards. Because the hazard is the conditional probability to have the event, given that you are still event-free at the beginning of that year. And of course then, because here we talk about not having the event, we have 1 minus the age over the different years. So in the first year, we have in total 146 individuals. There was 1 individual that died, so it's 1 over 146. But now comes the interesting thing. In the second year, 5 individuals were censored already. We don't know what happened with them. So the only thing we have to do is to say, well, there were 2 observed deaths out of 140, and not out of 145, and so on. And then we can do this for all the different years, and that is what the Kaplan-Meier is about. There is, however, one very important assumption for the validity of this estimate, namely that the censored individuals can be represented by those at risk. We say something about the probability to die, and we need to say something this is a way how to deal with the censored individuals. Basically, the ones that are censored, they're no longer followed, but everything that's happening after the censoring of an individual can be estimated based on the individuals that are still observed. Okay, so I told you already there's the one-to-one relation. So once you know the hazard, you can also estimate the risk or the survival probability. And this is in fact the hazard of the Kaplan-Meier. You've seen this formula on the previous slide, and here you see it in red occurring as well. But it's also the basis of the most important regression model in time-to-event analysis, and that is the Cox proportional hazards model. So in the proportional hazards model, basically the time component and the effect of the covariables are separated in a very specific way. In an elegant way, it doesn't always hold, but this is the most frequently used way, at least in the medical field, to quantify the effect of covariables on the hazard, and indirectly also on the survival curve. So now we'll move to competing risks. What are competing risks? In the previous slides, I told about censoring, and I said, well, censoring, some individuals are censored because they were not followed long enough. They may still have the event in the future, but it is not observed in our dataset. Competing risk is slightly different. This is an event that prevents the event of interest to occur, or it changes the risk of the event of interest in such a way that we really need to take this into account. But in the examples that I use, and that's also the most frequently occurring example, it's number 1, that is the one of interest. Here's an example. It's basically the same idea as what I showed before with the Kaplan-Meier, but now in the Kaplan-Meier we have seen that the mortality had gone down after 1996. These were HIV-infected individuals. After 96, powerful treatments became available. So this reduction in mortality is probably because of the introduction of therapy. And then you would expect this reduction in mortality mainly to occur in the AIDS-related mortality. So for that, it is interesting to split things up. And this is a typical competing risks setting. So if someone dies from a liver-related issue, for example, then he will not die from an AIDS-related complication. Or if someone dies from a natural cause, cancer, heart attack, whatever, then he will not die from AIDS. Here are the curves. So each row corresponds to one of those time periods. So up till 1996 and after 96, the lower row is after 96. And there are two different groups in this analysis. Hepatitis C co-infected individuals and HIV mono-infected individuals, but that is not that important. What you do observe indeed is that in the second period, it's mostly the AIDS-related mortality that has gone down. And for the other causes of death, it is all less clear. So this is the introduction to what competing risks are. So we go from the classical survival analysis setting, which you could phrase like we all die at some point. So in the end, the Kaplan-Meier curve, which starts at 1, will go down to 0, because in the end, nobody remains alive. But the interest is in finding out why some individuals die earlier than others. In a competing risk setting, we have something extra. So we are not just looking at mortality, but we are looking at different causes of death. So we do not all die at the same age, but we may also die from a different cause. We can go one step further. And say, well, life is also richer than that. We can also look at intermediate events. I'm not going to say anything about this in this presentation, but then you would end up with a multi-state model. So then you would include intermediate information to describe the whole process from, well, in this case, birth until death, but it could also be from HIV infection until death. Let me make a little bit of publicity. So I have written this all down in a book that was published in 2015. And so if you want to learn more about competing risks and intermediate stage or multi-state models, I recommend you to have a look at that book. So the rest of this presentation will be about competing risks. And how do I deal with them? Well, in fact, there are 3 different approaches, and that is the main purpose of my presentation, to explain those approaches. One is to treat individuals that experience the competing risk as censored and to interpret them as censored. I will give an example in a moment. The second approach is to treat them as censored, but interpret them as competing risks. And the third one is to ignore the occurrence of the competing risk in the estimation. They stay in the risk set forever, which is in fact a competing risks approach, even though you may not think so because you ignore the occurrence of the competing risk. And let me start with a simple example. Time to staphylococcus infection during hospital stay. So the time origin, individuals become at risk at hospital admission, and then 2 things can happen. They can become infected while staying in the hospital, or they can be discharged from the hospital without infection. And here, 2 different questions can be asked, 2 different study questions, and each of them may be interested. It just depends on your research purpose. What are you interested in? So the first one is what I would call the biological question. It's about etiology. You want to see what is the actual infection risk in the hospital from which we have data. And then basically you're saying, what would happen if everyone stayed in hospital? How many infections would we observe over time? What is the probability to become infected within 1 week, 2 weeks, and so on? So then you only look at hospital as endpoint, and the competing risk is not of interest. That is what I call the marginal distribution, or the net risk. The other question, which is relevant as well, is to quantify how many individuals actually do get infected in the hospital. And once you leave the hospital uninfected, you're no longer at risk. That is the competing risk setting, in which there are 2 competing events. So if you are discharged from the hospital without infection, you will never get infected in the hospital. So they are mutually exclusive events. So you could also say, The marginal distribution describes a more hypothetical example, hypothetical because it doesn't correspond to the data that we have, whereas the clinical question quantifies what we actually observe. So here, in fact, these are the same data set as I used before. So these are the numbers of events, and earlier I called them censorings, but here they are discharges. How do I estimate the probability to have an infection within 6 weeks after hospital admission? Well, in fact, it's very easy as long as there are no censored data. It's just a frequency. So within 6 weeks, 40 out of the 146 are observed to become infected, and 47 out of 146 are observed to be discharged. So what is important to observe here is that individuals with a competing event continue to be included in the denominator. So this is what I mentioned before, one of the approaches to competing risk. Basically, we ignore the occurrence of the competing risk in the estimation. Individuals that are discharged remain in the denominator. The marginal estimate, so estimating what would happen if everyone stayed in hospital, then the approach today is to look at the Kaplan-Meier. This is the marginal distribution, and individuals that are discharged are basically treated and interpreted as censored. It's not a competing risk because we are quantifying what would happen if everyone stayed in hospital. But I will remind you again, it is the important assumption is that the censoring is unrelated to the event of interest. In fact, so they are both relevant questions, and you may even, the answer to a question may even depend on which question is asked. So suppose we have two hospitals, A and B. In hospital A, say the infection risk is much higher. So the staphylococcus is much more prevalent in hospital A. So then for the marginal distribution, you would conclude that the risk is higher in hospital A. But suppose that in hospital A, individuals are discharged much more rapidly than in hospital B. Then what you actually may observe is that in hospital B, more individuals do get infected because they stay in hospital longer. So the marginal distribution may be higher in hospital A, but the cross-specific cumulative incidence may be higher in hospital B. So this is the distinction between a marginal distribution in which it's not really a competing risk analysis because the competing risk is treated as and interpreted as censored, and the competing risk setting. And the example that I gave, I used the subdistribution approach in which the occurrence of the competing risk is ignored in the estimation. And that is especially easy here because we assume that there were no censored individuals. So now in the next section, I will sketch the two different approaches to competing risks analysis.
Basically, there are two different hazards that can be defined, and the hazard is the basis for estimation. So the first one is the cause-specific hazard, which is the conditional probability to have an event of a certain of the type of interest, say type K, given that you are still completely event-free. So you didn't have any of the events. The estimate of the cause-specific hazard is very easy. It just quantifies the transition rate to that specific cause. So how many individuals experience that cause at a certain time point divided by the number of individuals that is still event-free. For the risk, the cumulative probability, there is an estimator which is called the Ahnen-Johansson estimator that is most frequently used in this multi-state approach. It basically combines the estimate of the cause-specific hazard with the Kaplan-Meier that is obtained by combining all the different competing risks. So in the example that I gave before, I looked at mortality, but I looked at 4 different causes of mortality. And for each of those 4 causes, you can define the cause-specific mortality or the cause-specific hazard. And if you add those cause-specific hazards, then you end up with the overall hazard. Because basically dying is dying of something. So if you sum all the causes of death, you end up with the overall death. The subdistribution approach, though, is a slightly different approach. And this is the example that I gave before. So in the subdistribution approach, we ignore the occurrence of the competing risk. Individuals with the competing risk remain in the data set. Basically, you can say they have the event of interest at time infinity. So theoretically, you would write it, you could define it through a random variable, say t star k, which is, so the event time is t if the event is of the type of interest, but it is infinity if a competing event occurred. And if you write the probability that t star k is smaller than or equal to t, that basically means the same as the event of type k occurred before time t. And we can also define the hazard of this new random variable. So the subdistribution hazard, it's the same type of definition, but now with respect to this new random variable. What changes, however, is if we look at the condition. So before the vertical line, so the t star k is t, is basically the same as we had before. It means that there was an event of type k at time t, but the condition that t star k needs to be larger than or equal to t, it can be either of two things. Either the individual didn't experience an event yet, so t is larger or equal to t, or a competing event had happened already. And that is exactly what is meant by an individual remains in the risk set. So then he is still at risk of even though in practice it doesn't occur, he is still considered to be at risk for the random variable t star k. So you could say they remain in the risk set forever. I write forever within quotes because it's not really forever. If there's additional censoring due to short follow-up, loss to follow-up, whatever, you need to use a slightly more complicated approach, but this is the basic idea. And again, just like before in the standard survival setting, the one-to-one relation with the crude risk is holds. So we can, for example, also use a Kaplan-Meier type estimator. With the only difference now that individuals with competing event are not treated as censored, but they remain in the risk set. For regression, as I said before, regression is often based on the hazard as well. And now that we have defined two different types of hazards, we can also perform two different types of regressions. And I will give an example in the final section. The cause-specific hazard. With the cause-specific hazard, individuals with a competing event are censored, so it's basically fitting a standard Cox model. However, the interpretation is different. What is quantified is the relation between the covariables and the cause-specific event rate among the event-free individuals. It's not the relation of the covariables and the marginal event rate, the event rate that would be observed if the competing event did not exist. So it's not a marginal hazard, unless the progression to the competing risk is completely independent from the progression to the event of interest. And that hardly ever occurs in practice. The example that I gave with Staphylococcus infection in the hospital, maybe that is an example where you could argue that this is indeed the case. So then indeed you could not only formulate those two research questions, but you could also solve them based on the data that you have. If the infection is a random process, unrelated to disease severity or the reason why you are in the hospital, then you could say indeed that discharge and infection within the hospital are unrelated events. The subdistribution hazard, and a specific case of this is the fine and gray model, which is not a proportional Cox model, but a proportional subdistribution hazards model. In a subdistribution hazard approach, individuals remain in the risk set. The nice thing about the subdistribution hazard is that what you obtain from your Cox model have a one-to-one relation with what is obtained on the cumulative scale with respect to the risk. And this is not the case with the cause-specific hazard. I will come back to an example of this in a moment. Okay, so the last part. I will go through all the things that I introduced again in a slightly different way. And let me start by giving a table. So these are all the things that I introduced, and that is a lot. In a standard survival setting, we only have one hazard and we have only one risk. Now, in a competing risk setting, we could define 4 different types of hazards. The marginal hazard, the cause-specific hazard, the subdistribution hazard, and in fact also the overall hazard, which is the hazard if you combine all the competing events. So if you look, for example, at overall mortality. So let me go through them one by one again. So the marginal hazard first. Think of the example that I gave with the infection in the hospital. The marginal distribution quantifies what would happen if nobody were discharged. And it will quantify the rate of infection in a hospital. It will quantify how dangerous staying in the hospital is with respect to infection. It is estimated with a standard hazard estimate. If an individual is discharged, he is no longer at risk. And this is the basis of the Kaplan-Meier estimate of the net risk or the marginal distribution. However, as I said before, and I cannot emphasize this enough, there's one important assumption: individuals that are censored can be represented by the ones that remain at risk. And otherwise, you can compute the Kaplan-Meier, but it has absolutely no meaning. Let me show this by example. And by the way, in this example, I will argue that the assumption doesn't hold. So I will show that, or show not formally, but I will argue that indeed the reason of the competing risk, that a competing risk occurs for an individual is related to progression to the endpoint of interest. And we can show this if we have additional information. The problem is we need independence for the Kaplan-Meier to be valid, and that can never be tested for. Very briefly, this example. We are interested in the time from HIV infection to AIDS, and we consider 2 different populations, 2 different risk groups, namely men who have sex with men and injecting drug users. However, there are many individuals that died before AIDS diagnosis. Well, what we can do is just not think about anything and plot the Kaplan-Meier. If an individual dies before AIDS, he is censored, and we compute the Kaplan-Meier. Once again, the assumption is that those alive without AIDS can represent the ones that died before AIDS diagnosis. This is what we get. Well, it's not the survival curve, it's 1 minus the survival curve. So what you observe, for example, 8 years after HIV infection, based on this Kaplan-Meier, men who have sex with men have a probability of around 50% to develop AIDS, whereas injecting drug users have a probability of around 20%. So if you believe this, you would conclude that if you are HIV infected, it's highly recommended to start injecting drugs, because the risk of developing AIDS is much lower. But of course, nobody believes this. And of course, the reason why you get this difference in estimates is because of the pre-AIDS mortality that is clearly related to progression to AIDS. So here we have the information on the causes of pre-AIDS mortality, and this mainly occurred in the injecting drug users. And if you look at the reasons, some of them are clearly related to progression to AIDS, but they never had an official AIDS diagnosis. And then the Kaplan-Meier is not valid. So that was about the marginal distribution. For the competing risk analysis, I introduced 2 different types of hazards. And in fact, both can be related to the cause-specific cumulative incidence, the crude risk, so the risk, the cumulative scale, but in a slightly different way. I didn't say how they are related in detail for the cause-specific hazard. For the subdistribution hazard, I said it more or less. But that doesn't matter for the moment. Another important question is, which one do I choose? And I will come back to that in a moment. So in a competing risk analysis, the occurrence of the competing risk is seen as a separate event. It's not seen as a censoring. It's not seen as a censoring occurrence. The important thing, and that is essentially different from the marginal analysis, individuals that are censored by the competing event don't have to be represented by the ones that remain at risk, because since the competing risk is seen as a separate event. So we don't need to worry about independence like what we need to do with the Kaplan-Meier. And that is something that many people find confusing. So you can estimate the cause-specific hazard. You don't need to make the assumption of independence of the competing risk and the other event types. It just quantifies the transition rate to each of the endpoints. So the cause-specific hazard, it's a basis for the Allen-Johansson estimate of the crude risk. And only if censoring due to the competing event is independent, then what you estimate can also be interpreted as a marginal hazard. But then still the next step is different. For the risk, for the cumulative probability, for the marginal analysis, we compute the Kaplan-Meier. For the cause-specific analysis, we compute the Allen-Johansson estimator. So the Kaplan-Meier is the probability, say, to have infection in the world in which nobody is discharged, whereas the Allen-Johansson estimator quantifies the probability to have an infection in hospital observed. These are essentially different quantities. Typically, the Kaplan-Meier goes down from 1 to 0. Think of mortality. In the end, we all die. Whereas the cause-specific cumulative incidence, which usually is plotted starting at 0 and then going up, never goes up to 1. The subdistribution hazard was the other one, and that one has the one-to-one relation with the crude risk. Well, this is, why would we worry about this choice? Well, there's one reason, and before going to that example, let me just give another very brief overview of what we have done with the examples. So, spectrum and causes of death, the first example, it's a completely competing risk analysis. Marginal analysis, thinking about what would happen in AIDS-related death in a world in which other causes of death do not exist is absolutely not relevant. Second example, we can think of a marginal analysis, but we can also define a competing risks analysis. And the third example is an example in which we are interested in a marginal analysis, but based on our data, we cannot come up with reasonable estimates. ACS here stands for Amsterdam Cohort Study, so that is where the data came from. Okay, so this is a question that is often asked, and many people, there are many papers about this as well. So do I choose the multi-state approach? Do I estimate the cause-specific hazard as basis, or do I use the subdistribution approach? So do I use the subdistribution hazard as basis? In a regression setting, do I fit a standard Cox model, or do I fit a fine and gray model? Both are fine in the presence of competing risks, but they quantify slightly different things. And I think this is best explained by means of this example. Suppose, I mean, this is not completely true, but suppose, so there was a change in the mortality after 96 because of the introduction of CART. Suppose that the therapy only reduces the AIDS-related mortality. It has no causal impact on the other causes of death. So that means that there are no side effects neither. Then what you would observe, say for the natural specific mortality, so the second cause of death in this figure, that wouldn't change after 96. If you are at risk, the probability to die from a natural cause doesn't change after 96. However, if you look at it at the cumulative scale, because if you no longer die of AIDS, you will die of something else in the end. In our data, this was not clearly visible, but of course, in the end, you will die of something else. So the natural mortality, what you actually observed at the cumulative scale, the probability to die from a natural cause, say cancer or a heart attack, will go up. If you no longer die of AIDS, in the end, you will die of something else, and that may be cancer or a heart attack. So with respect to the subdistribution hazard, you may observe, if you have long enough follow-up in your data set, you will observe that the hazard of the other causes of death will go up. for the cause-specific hazard, because the card itself, in my assumption, has no causal impact on the natural causes of death, it doesn't matter, but for the what is actually observed over time, and that is what is quantified in the subdistribution hazard, we will see a change. So that's basically what I say here in the example, so I'm not going to repeat this again. For the actual computation, so the subdistribution hazard has the nice property that it has a one-to-one relation with what's happening at the cumulative scale. So if you want to attach a number to this, the difference between before and after 96, it is more elegant to use the Vining-Gray model, to use a model based on the subdistribution hazard. But we can obtain predictions, we can obtain estimates of the cause-specific cumulative incidence, the crude risk, both based on the cause-specific hazard and based on the subdistribution hazard. I'm almost at the end. I want to end with one example. I have a couple of examples, but I can only choose one. So I told you before, there's a lot of confusion with respect to the interpretation. And this is an example from my own life. I was asked to be a member of a PhD committee, and I read the PhD thesis. It was written by a PhD student in statistics, by the way. And she used this example. So individuals that had bladder cancer, they were treated, and then the endpoint of interest was relapse of bladder cancer. And they looked at males and females. So the left-hand figure gives the crude risk of relapse of bladder cancer, the probability to have a relapse of bladder cancer over time. There's a competing risk though, mortality from other causes, death other causes. And with respect to bladder cancer, we see that males have a lower risk than females, whereas for the mortality as a competing risk, this seems to be reversed. So, of course, I think everybody will start wondering, maybe the bladder cancer risk is lower, the relapse risk is lower in males because they are more likely to die from something else. So what would you do? So you are interested, basically you are interested in the risk of bladder cancer as a relapse in a world in which you cannot die from something else. So what you could do, what you could think of, is say, well, let's do the Kaplan-Meier and see what's happening. You see that the curves are almost the same. So the solid curves are the crude risks, the gray curves are the net risks for relapse. But I told you a couple of times during my presentation, this Kaplan-Meier only makes sense if we can assume that mortality and relapse are completely independent mechanisms. And this is what was written in the thesis. So the gender difference is also present in the Kaplan-Meier curves. And the cause-specific cumulative incidence, or the crude risk, and the Kaplan-Meier are almost the same. Hence, the difference in relapse by gender cannot be explained by the larger competing death rates for males. Every time when I read such a statement with respect to competing risks, I need to sit down and I need to think about it for 15 minutes or maybe sometimes even longer. It's very easy to be fooled by this. This statement is highly controversial. Why? Well, for a couple of reasons. I told you before. So what does the Kaplan-Meier do? It tries to compare the marginal distribution. So it tries to estimate time to relapse for males and females, but it's only valid if death is completely unrelated to, death from other causes is completely unrelated to relapse. And that is a very strong assumption and it's unlikely to hold. The fact that they are almost equal, by the way, is because there is very little mortality due to the other causes during the first 40 months. So the first 40 months up till a year, that is exactly the period in which the relapses mostly occur. And there were very few deaths. And then basically, of course, if you don't have competing events, you are back in the standard survival setting. Another thing we could do, remember the curve. So I said, well, maybe the lower relapse probability in the males is explained by the higher mortality. Well, for the Kaplan-Meier, we get that the difference is still present. You could, of course, combine both event types. So I say times here, but it must be types. If you combine both event types, the curve for males and females will become similar. But that is, again, a highly controversial activity. Basically, if you want to interpret this as the probability to have a relapse, basically what you are saying, so the probability to have a relapse in the world in which competing death didn't occur, then basically you are quantifying, you are assuming that the individuals that died would have progressed to relapse right after, because you are combining the event types. Individuals that die are given an event as well. But if you want to interpret this as a time to relapse estimate, basically what you are saying is that when they died, they had a relapse. Relapse was not observed, but you basically assume that it would have been observed right after. So basically, the only thing we can conclude with certainty is the competing risk statement that females have a higher relapse-specific cumulative incidence than males. And if we want to conclude anything else, we need to make strong assumptions. That's it. Thank you very much for your attention. I mean, as I said at my introduction, interpretation of competing risks is a very difficult thing. I also introduced a lot of concepts, but I still think it is important to introduce all of them, at least to get a little bit of a flavor of what competing risks are about and what are the different approaches. Here are some references to literature, including the book that I wrote a couple of years before. We also wrote a tutorial in Statistics in Medicine on competing risks. And now it's time for questions.